Hi everyone, welcome to today's QMNET seminar. That's a informal seminar series loosely based at the University of Melbourne about any quantitative method techniques and for researchers in various fields. We're lucky to have Christina Kreisch and Miles Cranmer today from Princeton. So a little bit about them before I hand over. So Miles is currently a DeepMind research scientist intern on the structured intelligence team and a fourth-year PhD candidate, an NSERC fellow at Princeton University Astro. His thesis focuses on neurosymbolic learning for dynamical systems, while Christina obtained her PhD in astrophysics from Princeton University in 2021. And while there, she was an NSF graduate research fellow, presidential fellow, and Charlotte Elizabeth Proctor Fellow. And she has certificates in statistics and machine learning and computational and information science from Washington University. And I'm looking forward to that talk. So thanks for coming.
Yeah, thanks so much for that introduction. So today we'll be discussing some work we've done on histogram pooling and symbolic regression. We're going to be switching on and off in terms of speaking. So I'll be talking at the beginning, then Miles will take over, and then I'll take over at the end. All right, there we go. So let's start from the beginning. How does the universe even work? So here we have our galaxy, the Milky Way, and we're zooming out from the center. And the Milky Way is situated in a cluster of galaxies within a broader field of galaxies. Now, this cluster of galaxies is also situated in an even denser cluster of galaxies, and we call this a supercluster. Now, the supercluster that our Milky Way galaxy is located in is called Laniakea. Sorry about that. There we go. Now, what are cosmic voids and how do we find them? So if we take a snapshot of our universe, as if we're looking out into the universe, the night sky, but with a very nicely powerful telescope, we're going to see an image that looks like this. These bright regions are galaxies, and you'll notice that you see these clumps of galaxies. These are those clusters, the galaxy clusters that I was showing you in the previous video. You'll also notice that this isn't a random distribution. You'll see kind of some string-like filamentary structures, and we call this the cosmic web. Now, within these filamentary structures and clusters of galaxies, we have these vast empty regions of space. Now, we see a few galaxies within them, but they're really mostly empty. And we actually call these regions cosmic voids. So we may find a cosmic void here, here, there, all of these underdense regions. Now let's go to a video again. Now, underdense regions, which are cosmic voids, are blue, and highly dense regions, so superclusters, are in red. And you'll notice that due to gravity, we actually have an outflow of galaxies from these underdense regions into these dense regions. And so voids have an interesting impact on the dynamics in the universe. And again, you'll see this from another perspective in this slide. So again, you can see all of those clumps of galaxies creating clusters of galaxies, and the cosmic void here, which has very few galaxies in it. Now, how do we even find these voids? You know, when we take images of the universe, we're observing galaxies, but these cosmic voids, by definition, hardly have any galaxies in them. So how do we even find them? Well, what we do is we start with our galaxy field, which I'm showing you here. Each dot is a galaxy, and of course, the denser regions are those clusters of galaxies. And then we perform a Voronoi tessellation. Now, what this Voronoi tessellation does is it says, okay, every region in space that's closest to a given galaxy, we're going to put that in a cell containing that galaxy. And we do that for every single galaxy in this field. Now, after that, we perform a watershed transform. And in the end, this essentially merges basins together, those cells, to create a larger basin. So you can think of it like this image at the right. You start with these tiny cells, and then you can imagine pouring water into them. So imagine the cells are tiny little puddles, and it keeps raining more and more. And eventually, it rains so much that those puddles form an even larger puddle and a much deeper puddle. And you can keep filling up those tiny little basins until they form one giant puddle. So that's essentially how we find these cosmic voids. These bumps in these regions are those clusters of galaxies, and these troughs are the underdense regions. And because we're building up these cosmic voids, looking at the densities, we're able to form these voids, these cosmic voids, in a way that really captures this hierarchical pattern of the cosmic web. We're able to get a detailed shape of those voids rather than making any assumptions about their shape. And for example, if we're going back to that snapshot I was showing of the universe, perhaps this oblong cosmic void might fit somewhere like right here in that image. Now that's all great, but in astrophysics, why do we even care about this? Well, we have a model of the evolution of the universe, and there are several key parameters that help govern how we expect the universe to evolve. Now, the structure, the galaxies that we see in the universe, can help us put constraints on that. That's happening because after the early universe, the universe cools to such a point that these stars and galaxies form. And eventually these galaxies attract to each other, like I was showing you in that video at the beginning, and form these clusters of galaxies. And so by looking at that distribution of galaxies, observing those filamentary structures, we can basically put some constraints on these cosmological parameters and therefore our cosmological models. And so by looking at cosmic voids, which are the underdense regions of the universe and which capture this nice hierarchical pattern of the cosmic web, we hope to be able to put tighter constraints on these cosmological parameters. So let's return to the image with the density. So again, purple, black, blue, this is corresponding to underdense regions. And red and green are corresponding to denser regions. Now again, since this is an underdense region, this is corresponding to what we could consider a cosmic void. And let's just talk about a few key features of cosmic voids. So one feature that cosmic voids have is something called density contrast. Now, what that means is basically the depth of the cosmic void. So you can think of it as what's the difference between that center of the cosmic void, so the most underdense, and basically right outside the cosmic void where it's much denser. So for example, here, you can see a much stronger set of contours in the coloring. That means that this has a higher density contrast than this portion of the cosmic void here, which doesn't have as much change in the coloration. The next feature of cosmic voids is their ellipticity. So of course, that's just their shape. The next feature is radius, so their size. Now, central density is another feature we can take a look at. That's the actual depth of the cosmic void at the center. And finally, you can also look at something called the void's children. Now, imagine this right portion of the underdense region. Imagine this is a cosmic void. And you can see these two slightly more underdense regions in it. Those two regions could be considered children of that larger parent cosmic void. So that's shown in that ellipse there. Now, what we're interested in, as I was mentioning earlier, is we really want to go from these cosmic voids and their properties to predicting cosmological parameters and putting nice constraints on them. So to do that, we use a suite of simulations called the Quixote simulations. And this is a really wonderful suite for machine learning. It has 44,100 full n-body simulations, and they're explicitly designed to quantify the information content in cosmology, as well as provide enough statistics to train machine learning algorithms. And so just to visualize this data a bit more, this is slicing through an image cube of the universe. You'll notice these filamentary structures coming in and out. And again, those bright dense regions are these galaxy clusters. Now, within these filamentary structures, you'll see these dark regions, and they take all different shapes and sizes. These are the cosmic voids that we're focusing on in this talk in terms of our astrophysics application. So in order to analyze this, we can use deep learning. It's really great for finding complex relationships and modeling them. But, in astrophysics, something that's really important is understanding these relationships and interpreting them. And deep learning can often be challenging to interpret. Now Miles is going to take over.
Thanks, Christina. Can you hear me okay?
Yep, we can hear you.
Okay, so deep learning is kind of like the classic toolbox of deep learning is very good at tabular data. So for tabular data, you use like a multilayer perceptron. For images, so that is like a convolutional neural network, or sequences. So these are recurrent neural networks. So kind of like all of if you think about like all the data sets available to apply different numerical methods to, deep learning really excels at these specific tasks. So tabular, images, sequences. But really, the natural world has a lot more structure than this. It's not just grids. Like the natural world is best represented by maybe like a set of objects or a graph. So a set with edges connecting different elements of the sets. So whenever we project stuff onto a grid, it's really kind of like an artificial data pre-processing step that we kind of like artificially apply to the data. But so like, why isn't there deep learning that kind of like works on these natural data structures rather than on this pre-processed version? So this is where graph neural networks come into play. So it's this type of neural network that can work on a very kind of generic type of data. So like a generic graph structure. A graph neural network works on that, whereas like a CNN would only work on images. So one of the really nice things about graph neural networks is they also have a very interpretable internal structure, and this is kind of like very useful for us as astrophysicists, in that we kind of want to understand like what the model's doing. Like if you present some deep learning model at an astrophysics conference, like maybe half the audience is gonna think it's like kind of bullshit. So you really need to kind of show them like what is the model actually learning. And I think this is what graph neural networks are also really, really good at. So we have this paper from 2020 that kind of looks at graph neural networks trained on a simple force, like n-body problem, and you can actually extract the analytic force laws from the graph network. So they have, because you're not kind of like pre-processing data, because you're working with the natural structure of the data, it's much easier to interpret kind of what type of processing it's doing. So the way a graph network works is you can think of it as 3 different modules. So any graph you can represent like this. So you have, can you see my cursor, by the way? Okay, so you have, so this is a graph. You have nodes in the graph. So those could be like particles in a data set. You have edges in the graph. Those could be like forces between particles, or really like in a more generic sense, like they could be messages passed between agents in an RL problem, stuff like that. And you also have the global attribute, which is kind of independent of the graph structure. It's kind of describe something about the whole graph. So that could be like a background magnetic field. It could be some like conditional parameter. So this is a generic view of a graph. And a graph network is kind of any model that can take these three sets. So you have a set of nodes, a set of edges between those nodes, and a global vector. And you output a new global nodes edges. So any kind of structure that works between two graphs is a graph neural network. So the way it actually works is you have these different modules. So basically the edge block works on updating each edge. And so these are the actual functions. The way it usually works is you give it the current vector describing that edge, the two nodes, and maybe the global vector, which is kind of like a context variable. And this function would be like a multi-layer perceptron or something, and it would update the edge. And you do something similar for the node attribute, but you take the sum of all the connecting messages into this variable, and you pass that through the node update function. And so what this does is it makes your model kind of invariant to permutation, and it allows you to learn functions on graph in a very generic way. So, and you do something similar for the global update. And so this framework, it really lets you learn kind of like any function on a graph. Like people are even doing, like they learn to manipulate like Atari games at the like individual bit level. Like these graph neural networks are very, very expressive, and they can model a lot of problems. Now, for us in particular, we're interested in cosmic voids. And so for us, the nodes in the graph are cosmic voids. So we treat those as nodes, and the nearby voids, we kind of assign these edges between them. And that helps, that's the input to the graph network that it can kind of learn to predict global properties of the universe. I think I'm gonna skip this one. But basically, when you work with cosmic voids to predict properties of the universe, normally what you do is you look at a histogram of distances between voids. So you take all the voids, you compute distance from one void to another void, and you basically take a histogram of all the distances. And this tells you, okay, what's like the most common distance that two voids are from each other. And so this is called the void correlation function. And basically just by looking at how far voids typically are from each other, you can infer global properties of the universe. So this is one type of analysis that people do. And there's no machine learning in this. This is just like what people commonly do manually to analyze this type of data. Now, actually, let me skip this one. So what we do is, instead of kind of applying this manual analysis where you kind of you look at distances between voids, compute a histogram, and kind of use that to predict properties, what we do is we use a graph neural network to kind of infer the cosmological parameters. And more specifically, we use something called a deep set. So a deep set, it's literally just like a graph network, and you remove the edges. So what it is, you can think about every xi is like an element of a set. So you have some set of elements. Every element in that set is described by a vector. You then take each vector and you map it through some function g. And this might project it into a higher dimensional latent space, it might project it to a lower dimensional latent space. But that's the encoding step. You basically encode every element of the set. the next thing you do, you apply a permutation invariant aggregation. So summation is the most common one. So you basically, you sum in that latent space, or maybe you take an average in that latent space, element-wise. So you take every element of your vectors, you do a sum, or like a mean, or a max, or something. And the output of this is kind of like one summed latent vector. And you basically map that through another function to predict some global property of that set. So that is the function f. So just by learning these two functions, g and f, you can learn an arbitrary property of a set. So this is called the deep set. They're also like a very expressive architecture for when you don't have kind of natural edges in your data set. So we use deep sets in this analysis. For us, the set is these void structures in cosmological simulations. And the y vector here, like what we want to predict, is cosmological parameters. So these are things like what's the average component of the universe that is in dark matter. Like that's one cosmological parameter of the universe. So we want to predict by using these voids, which is a set, we want to predict, okay, what's the dark matter content of the universe? So we want to do it with a deep set. Now, the problem with this, and this is what astronomers will come at us at talks, is like, it's not interpretable. Like you use this deep set, you use this GraphNet, how do you know what it's doing? Like, how do you know if you apply it to real data, it will just like, it won't work at all. And this is a major problem. And so something to consider is when you have this deep set, you are commonly projecting it to a very high dimensional space, summing in that space, and then maybe decoding to a smaller dimensional space. So when you project to this very high dimensional space, like it's very hard to interpret what's going on. Like it could be really doing anything. Like it could be, it could literally just be like concatenating vectors in these massive vectors, and then the second function is like doing some joint operation. So what you really want, you want to work with a small dimensional space. So you want the output of G to be very low dimensional. So maybe you have elements in your set, you describe them with a single number. That's very interpretable. If you describe every element in a set with a single number, that's like very interpretable. You can kind of understand what the deep set is doing. The problem is the permutation invariant operator, this is normally just like a sum. If you're just summing a bunch of scalars, there's like, you can't really get a lot of information out of that. So what we decided to do is to, instead of a summation, use a histogram, because this is what people do in astrophysics. So there's many different problems where you have like a set of objects and you take a histogram of some feature and then you do an analysis on that histogram. So rather than summing these large latent vectors, now we take a histogram along each dimension. And the reason we do this is because you can get much more information through that aggregation than you can with like a sum. Like a sum, it just collapses it to a single number. But if you take a histogram along one dimension, you can get like every single bin of that histogram is a number. So you can get much more information through. So we say when you do a deep set operation, you basically want this row operator, which is the permutation invariant operator. You want it to be a histogram, basically, like an element-wise histogram, because that will let you describe G with like a single number as the output, but it'll get a lot more information through for the function f. So we have this soft, it's like a soft histogram, and the reason it's soft is so you can get gradients through your algorithm. So it's basically like you took a histogram and you just smoothed it out. So this paper is in the simulation deep learning workshop. We're going to turn it into an astrophysics paper as well. So read that paper if you want more details on this. This is a diagram of how it works that might help explain it a bit better. So again, you have this set of objects. So maybe you have like a circle, square, star. Each object is described by a vector. And like I mentioned earlier, there's not many deep learning architectures that will let you do operations on this. Like you can't apply a CNN to a set. So what you do is you encode these vectors to some latent space, and then you do an aggregation operation. So what people normally do is a sum pool, which collapses it. But what we say you should do is a histogram. And that lets you get a lot more information through, even if you have a small dimensional latent space. And so the reason for that is you get more interpretable results. So the second thing we do is something called symbolic regression. So we take this learned model and we apply something called symbolic regression to kind of understand what that number is that our model has learned. So symbolic regression, it's another machine learning algorithm. So you want to fit a model to predict a number y given a bunch of numbers x. But the basis of this machine learning model is analytic equations. So, you have this vector and you want to predict y, but you search for different analytic expressions that give you that relationship. So if I have this data, like this is my x-axis and y-axis, I might, if I'm like manually doing symbolic regression, I might say, okay, is this cosine of x? No. Is it sine of x? No. Exponent of x? Yeah, that's closer. So then maybe I start from there and I fiddle with that equation. Okay, exponent of x over 2? Yes. So that's kind of how symbolic regression works. And why do we want to do this? Like, why don't we just use deep learning for everything? So analytic expressions are a very good inductive bias for physical problems. Like so many rules in the natural sciences, particularly physics and chemistry, are described by simple analytic expressions. So this is like some physics 101 cheat sheet. So the question really should be like, why don't we use this as the basis of our machine learning models? Like we know it works so well. And symbolic regression kind of lets us do that. So there's this really cool article by Eugene Wigner called The Unreasonable Effectiveness of Mathematics in the Natural Sciences. He kind of points out all these weird connections between different fields that have like the same simple symbolic model in completely different fields. Like pi appears in the area of a circle. It also appears in the normalization of a Gaussian. Like there's a lot of weird connections like that. So, okay, still like why? So one, it is concise. If you find an analytic expression for a data set, it's something you can write on a piece of paper and people can just apply your model. It's very interpretable. You can kind of, it won't explain why the model learned it, but you can kind of start to see, okay, maybe this is why that model predicts it, and you kind of analyze it. Another thing we noticed is for physical problems, analytic expressions may generalize better to out of distribution data than neural networks trained on the same data. And this goes back to the point, symbolic expressions seem to be like a very good inductive bias for physics. So how does it actually work? So if I have maybe this expression, I can represent it as this tree, this binary tree. And then what Peiser does, it uses a genetic algorithm. So you go through this tree, maybe you take this multiplication operator, swap it with a division, maybe you replace this variable with this variable, and you kind of do step by step, you compute the accuracy of that equation, and maybe you keep going that way, or maybe you throw out the equation, switch to a different one. It's kind of like MCMC, but in this discrete space. And normally you do it with populations of equations, and you kind of evolve them, and it lets you explore this equation space. So the way you combine symbolic regression with neural networks is the following. First, you create a neural network for some problem. So like you want to learn some mapping between a data set and some number. You create a neural network, but you have the neural network have separable internal functions. So like a graph network, there's like the edge update function, the node update function. They're kind of separable modules you can kind of take out and try to interpret. Now, every one of these separable internal functions, you have to train it such that the input and output of that internal function is low dimensional. So their inputs and their outputs should be sparse. And the reason for that is that symbolic regression scales terribly with the number of variables. So by kind of constraining parts of your neural network to operate on low dimensional spaces, it makes it much easier to kind of take out that module and try to interpret it with symbolic regression. So you take this neural network, you train it, and then you apply symbolic regression. You try to kind of approximate every internal part of your neural network with symbolic regression. And at the very end, you compose these analytic expressions together, which gives you like a symbolic expression for your model. It's basically like you train a neural network on your problem, and now you want to find a symbolic expression that gives the same results as that neural network. Because if you can do that, the symbolic expression is much more interpretable, better generalization properties, etc. So yeah, there's a GitHub tutorial here if you want to try this kind of technique. And basically, yeah, we applied it to cosmic voids. Christina, do you want to take over again?
Yeah, sure, I can take over.
Okay, I'm gonna mute myself.
Oh, sorry. All right, sounds good. Yeah, so we apply this to cosmic voids, like we've been mentioning. And like before, we said that these voids have various different aspects, different properties that we can use. So things like the ellipticity, the size, and of course, they come in all different shapes and sizes. There we go. So as Miles was mentioning, these graph networks and in turn histogram pooling are really wonderful for being able to capture this inherent pattern that's in the universe, and even capturing in the spirit of ways that we analyze the universe already, for example, in that void correlation function that Miles showed you earlier. And so what we've done, and by using symbolic regression with these histogram pooling operators, is that we can actually get an output for G, and recall G is this parameter here in our histogram pooling. And this is a extremely interpretable equation. We can think of Z as an optimal feature for voids, where R is the void radius, this delta is the depth of the voids, and epsilon is the void ellipticity. And so just, by seeing the simple equation, we can even begin to interpret, okay, we see that the void depth is in fact seemingly the most important feature here. Of course, void radius we would expect to be important, but we see that depth is actually the most important here. And in fact, ellipticity is also important in this cross term with the size. And so by being able to use symbolic regression, we can extract these better features. And with this, we can try to put more optimal constraints on cosmological parameters. And so that's what we've done. So we, with this omega matter, which you can think of as just the amount of stuff in the universe, so the stuff that makes up galaxies, this is one of those parameters that informs our cosmological model. And we're able to basically predict this parameter with an error of 13%. Now, this is actually a really good error for this, in particular from cosmic voids. Because in classic analyses of cosmic voids, such as an idealized Fisher forecast, we can really only get 20% constraints on omega matter. So that's corresponding to this column here, these contours. This is using the exact same simulation suite and over 20,000 simulations to get that 20% error. Whereas by using an intelligent choice of operators, as well as how you formulate your neural network, we're really able to take advantage of the structure of the universe and extract further information about it, which helps us put, in turn, more informative constraints on cosmological parameters. And so that's why we're able to get this 13% error on that parameter. So in summary, we have shown you this new interpretable pooling operator, histogram pooling, that we've developed. And in particular, in cosmology and in astrophysics, as Miles was stressing, it's really important to be able to interpret those relationships. And in fact, there's many, many extremely nonlinear relationships in astrophysics. So being able to have a way to interpret them and extract them in an interpretable manner is really key to make progress. Now, graph neural nets and interpretable pooling operators allow us to learn these previously unknown relationships, since they take advantage of the data structure, and they offer a new way to extract this new information about the universe using tons of data. Currently, there's no existing analytic equations for void-based cosmology and putting constraints on these cosmological parameters. So this is really the first step in shedding light on these unknown relationships. And again, since these relationships are interpretable, they can be easily applied to data and used to extend theory. And of course, we've just shown you for astrophysics, but this could be applied to a whole host of different problems. Thank you, and we're happy to take any questions.
Thanks very much. That was really cool. I guess we can all give you some virtual clapping or even some physical ones if you have cameras on. So do we see anyone who would like to start the questions? Is that a thumbs up, someone wanting a question, or just a generic sign of happiness? Okay. I guess, so can I maybe ask about the simulation that you were using to train, this Kyoto simulation?
Mm-hmm.
So is that just running, say, like an n-body simulation, like pushing forward this system of galaxies moving around according to like what we know of the gravitational equations, using lots of different random starting points? Or is it something like changing the constants of, like, say, make gravity stronger in this simulation and weaker in this one, like looking at different universes? Can you maybe just tell me what?
Yeah, absolutely. So that's a really excellent question. It's both, essentially. So there's a set of, I believe, 15,000 simulations for what we call the fiducial cosmology. So it's exact same cosmological parameters, but the initial conditions are slightly different. So basically in a random manner. And yeah, as you were mentioning, we have these equations that we understand govern the evolution of the universe. So we utilize those to propagate forward where we start and go through time. Now, there's also two other components of the simulation suite. So there's a component where you just step a single parameter at a time. So that's really good for doing things like Fisher forecasts, for example. And there's, I forget how many thousand, but there's several thousand simulations for that. There's also a Latin hypercube set within this simulation where you have multiple parameters varied, And it's basically kind of like a random sampling of the entire parameter space and how they're varied. And there's also several thousand simulations for that, as well as low resolution versions, high resolution versions, and snapshots at different points in time that you can look at.
That's very cool. And I wasn't sure, are you feeding in, like, are you looking at a whole time series approach to this, or are you just taking a slice in time?
Yeah, that's another good question. It's a single point in time.
Yeah, I guess you don't have any way to get a time series on a useful scale looking at the universe, the real universe, so it's not very useful to have methods that rely on that data.
I mean, actually, that is useful, understanding how things evolve in time. Miles, feel free to chime in. I'm just giving thoughts that come off the top of my head. We just haven't done it yet, but I think it would be useful to do.
Yeah, that's because as you look farther and farther away, you see farther and farther back in history, right? So you could potentially use different like times in the history of the universe and kind of build your model to accommodate that. So like multiple times, and kind of use that, because we do have observations of, like, we don't have the same galaxy over multiple times, but we do have like different galaxies at different times.
Yeah, and it's also the case in astrophysics that you know, a certain object might be optimal at a certain point in time for constraining a certain cosmological parameter. And so it is useful to do these types of analyses where you try to figure out, okay, what point in time should I basically focus my survey in order to optimally constrain a parameter with a certain object.
Okay. I guess Pramod writes in the chat, excellent presentation. Thanks a lot. Thanks, Pramod. If there's no other questions, I might ask again about, this idea of taking a neural network and then summarizing it with symbolic regression seemed really cool. And that, just to check that I understand it right, is it kind of like this, like an autoencoder? Like you have this, you just periodically flatten everything down to a pretty small number of nodes, like different checkpoints through the network, and then try to do symbolic regression, say from the input space to the first checkpoint, and then from the first checkpoint to the second. Is that kind of what's going on?
Oh, that's interesting. No, it's much like dumber than that. Like that sounds very, that sounds like an interesting idea. But the way it actually works is like pretty simple. Where's the GraphNet? So if this is a GraphNet, I have 3 functions, and if it's like one GraphNet block, then I would have 3 multi-layer perceptrons. I would have the edge function, the node function, and the global function. So during training, those would be multi-layer perceptrons. But once I have the model trained, I basically take phi e and I like feed in random inputs, see what the outputs are, and then approximate that relationship with an equation. And that's literally it. Like you just try to approximate the multi-layer perceptrons with equations.
Okay, I didn't realize this was like a recurrent thing. Like those functions are being applied over and over again. Maybe I'm not getting this.
Well, so if it's like a single, like if it's just one GraphNet block, then it's only applied once.
Yeah. Okay.
So it would just be a function of however many input features to however many output features, and you just try to. So the reason you can't do straight symbolic regression is because you can't. There's no gradients if you're searching an equation space, right? That's the main reason you can't do pure symbolic regression. You have to start with a differentiable learning method, like deep learning, and then take those learned functions and take them piece by piece, trying to fit them with equations. You're basically like dissecting your neural network and trying to like replace parts of it with equations.
Yeah,
So
I heard
you
of.
do have to be a bit creative during this
Mm.
process, and kind of like you have to optimize simplicity of the equation versus accuracy of the equation. Yeah.
Yeah, I guess this genetic algorithm that you run inside the symbolic regression would be very slow, wouldn't it? Like without
Yeah.
gradients at all, and if
Yeah,
you
there's no
had
gradients.
a
It's
few,
basically like a brute force with
yeah,
it's a bit better than brute force. Yeah. And
yeah,
these spaces are huge. Like normally you would search for like 10 to the 10 equations, and you have to kind of consider, I mean, you don't search every single one, but you kind of try to explore that space. Like these spaces are very big, and
mm,
it's easier to kind of use the graph network to break the problem down into smaller functions that each have 10 to the 10 equations, rather than kind of learning all the equations at once, which would be 10 to the 10 cubed equations, right?
mm, mm.
So that's why it's easier to kind of learn it first with deep learning, and then cut it into smaller, easier to interpret pieces that you can try to interpret.
Do you get significantly different outputs? Like, I guess it's a random algorithm, a random search. So at the end of the day, you'll get this analytic equation for this physics, this astrophysics that you like, and the version you showed in the talk here was like a linear equation. And I guess if you run it again and again, you might get different things. Do you see that in practice? Like sometimes it's like exponential, and other times it's cosine, or is it
So
pretty stable?
yeah, so the genetic algorithm, like for that kind of complexity, it should always find that same equation. If you let the max size of the equation be very, very large, then it just can't explore that space fully to kind of like always get to the same equation. But for simple equations like that, and even slightly more complex, it can almost always find the same equation. But I will say, like, it also depends on the deep learning seed. So if you train a neural network and it finds like a different function, then obviously you might extract a different equation at the end. So you have to worry about that too.
Yeah, I did have a little smile when at the slide saying here we have interpretable results, but then there are some linear equations, like linear regressions, that are very uninterpretable at the end of the day, with lots of
Yeah, and I think this is the difference between like interpretability and explainability. Like interpretability is I can kind of say, when this changes, this will change in this way, and I can kind of like stare at it and see the contributions of different features, see if there's like a singularity. But explainability, this does not solve it all. Like explainability is kind of up to you to explain why that expression was discovered. Yeah.
I guess at a high level, the idea would be you guys go through this whole process, get some equations, and then go off and do some theoretical physics to justify something along those lines.
So actually, in the history of quantum mechanics, the Planck equation, it's this famous quantum mechanics equation. It was actually a function fit. Like he fit an expression to the data. And then later they kind of like in the development of quantum, they explained that expression. So like it has, like there's history to this process. Like you find an expression or some pattern, and then you try to explain it, and you develop a theory in the process. So the Planck equation is a nice example. Yeah, our advisor always uses that example. Yeah.
Very cool. I guess last chance for.
Hey, I've got a quick question. So I was interested in the histogram pooling thing. So if I understand correctly, this is sort of like a differentiable kernel density estimate. Is that sort of right?
I had that same question. It's the sum of Gaussian equations, right? More or less.
I think so, but it's a bit different because you're doing it in the latent space. So like it is a, is it? I mean, so it is a grid. Like you have to have a grid of values. So it's not a continuous kernel density estimate, but I guess you could say, it is like, you can kind of see, like these are the histogram edges. And you can see they're soft, and it's kind of like a kernel density estimate. You have a kernel over every histogram bin in a way. But it's important to note, like this is on the latent space rather than the input space.
Okay, so if it's in the latent space, could you explain again how it like makes your model more like interpretable?
Right. So the reason it does is because in a sum pool, you have many latent features to get to some accuracy, but the histogram pool, you could have like one feature, but since you're taking a histogram of that feature, you can get much more information through. And then you only have to interpret one latent feature instead of like 100.
I see. That's interesting. Thanks.
So you could think of it like concatenating the sum of a feature, the variance of a feature, the mean of the feature. It's like the most generalized form of that. You just take the histogram of that feature, and it gives you all the moments of that distribution. So it only has to predict one latent feature, and that is kind of like the description of that element in the set.
Right, so it's sort of like learning a distribution of your latent features instead of just like learning summary statistics, sort of.
Yeah.
I
Okay.
guess the sum version is kind of like the histogram with only one bin, right? So sort of generalizing over the number of bins.
Yeah, I think, well, no, the sum pool, because the sum pool is like you're summing the latents, but here you're counting the latents in bins. So I think it's slightly different than, but it's kind of similar, yeah.
Yeah, so Terence Speed had just written, thanks, interesting and challenging. Yeah, I was curious about your Julia and Python library, just because I'm interested in coding. How did you get, is it some like C code base that you've ported into both, or you're calling Julia from Python or something like that?
Yeah. So I kind of think of Julia as an alternative. Like a lot of people think of Julia as an alternative to Python. I think of Julia as an alternative to C++, kind of like a high level C++, because it is compiled using LLVM, which is like Clang uses LLVM too. So you can get the same performance, sometimes even better performance than C++ libraries. So yeah, it's a Python front end, which lets you kind of interface with other machine learning packages, and then Julia backend just for speed, because I didn't want to write it in C++. Yeah. And it's also nice because you can, it's very easy to like define custom operators, and you don't have to compile a new binary. You just like, it's just in time compiled, which is nice.
I'm always jealous how you physicists are so good at maths and so good at programming. It seems unfair in this world. Anyway, maybe I can say thanks one last time and stop the recording. Yeah, thank you for coming.
Yeah, thank you. Thanks.
Yeah, thanks a lot.